Imagine having thousands of puzzle pieces just completely dumped onto your table. But there's a huge catch. You have absolutely no picture on the box to guide you. You don't know what the final image is supposed to look like, or honestly, if the pieces even belong to just one puzzle. So, how would you even start making sense of that? Well, you'd probably start grouping pieces by color, right? Like maybe putting all the sky blue pieces in one pile and the green grass pieces in another. That intuitive process, grouping things by similarity, is exactly the problem unsupervised machine learning is trying to solve. Welcome to this explainer. Today, we're going to crack the code of unlabeled data. Here's our roadmap for today. First, we'll look at the magic of clustering. Second, partitioning data with k-means. Third, building hierarchical trees. Fourth, what to do when you just don't know k. And finally, we'll clear up the confusion between k-means and k-nearest neighbors. Let's dive in. Section 1. The magic of clustering. Grouping the unknown.
So when it comes to exploratory data analysis, clustering is kind of the ultimate tool in your toolkit. Formally speaking, clustering is an unsupervised machine learning technique. Its entire job? To group data points into clusters based purely on their similarity or dissimilarity to one another. Now, the absolutely crucial word here is unsupervised. There are 0 predefined labels. No human has gone through and tagged the data saying, hey, this is a cat or this is a dog. The algorithm is operating completely blind. It's just searching for those hidden patterns and underlying structures completely on its own.
Now, you might be wondering, why does this actually matter to us? Well, because clustering literally impacts our daily lives in massive ways. Think about market segmentation, right? That's how companies group consumers with similar buying habits to tailor their marketing. Or image segmentation, which powers things like medical imaging and computer vision. It's also used in document categorization to automatically organize massive libraries of text. And, crucially, it is the backbone of anomaly detection. That is exactly how your bank catches credit card fraud. If a transaction doesn't fit into your normal, everyday cluster of spending behavior, bam, it gets flagged. Moving on to Section 2, partitioning data with k-means, the flat grouping strategy. This brings us to the most famous partitioning method of the whole bunch, k-means clustering. It's elegantly simple and it works in 4 basic steps. Step 1 is initialization. You literally just tell the algorithm how many clusters you want, that's your k value, and it randomly drops k center points, which we call centroids, right into your data. Step 2 is the assignment step. Every single data point looks around and assigns itself to the closest centroid, usually calculated using a straight line Euclidean distance. Then, step 3, the update step. The algorithm looks at all the points in that newly formed cluster, calculates the exact dead center mean of those points, and actually moves the centroid to that new location. And step 4, repeat. It just alternates between assigning points and moving the centroid until those centroids completely stop moving. And that right there is when we achieve convergence. Behind the scenes, the math driving k-means actually has one single obsessive objective. It wants to minimize the within-cluster sum of squares, or WCS. To put that into plain English, the algorithm is constantly trying to make each individual cluster as tight, compact, and spherical as mathematically possible. It just wants to minimize the variance inside every single group. So how does k-means compare to its siblings in the partitioning family? Well, because k-means uses a calculated mean as its center, it's incredibly fast, but it's highly sensitive to outliers. A single crazy extreme data point can drag that mean way off. Enter k-medoids. Instead of a calculated center, it uses an actual existing data point as the center, the medoid. Now, it's slower for sure, but much more robust to outliers. And then we have fuzzy c-means. While k-means forces a hard partition, meaning a point belongs to cluster A or cluster B and that's it, fuzzy c-means actually allows a point to belong to multiple clusters at once with varying degrees of membership. It's absolutely perfect for capturing uncertainty and handling overlapping data. All right, Section 3, building hierarchical trees, clusters within clusters. But what if your data isn't just flat? Instead of making these non-overlapping groups, hierarchical clustering organizes data into a nested, tree-like structure, which we call a dendrogram. To build this tree, you really have to answer one foundational question. Are we building this from the top down or the bottom up? These are 2 completely opposite strategies. Agglomerative clustering is the bottom-up approach. It starts by treating every single data point as its own tiny isolated cluster. Then, it iteratively merges the closest pairs together step by step until everything forms one giant cluster right at the top. Divisive clustering, on the flip side, is the top-down approach. It starts with all the data just lumped into one massive cluster and then recursively splits it into smaller and smaller groups. Now, while Divisive handles global data structures really well, it is incredibly computationally expensive, like scaling at an exponential rate in the worst case. Because of that, agglomerative is way more commonly used. But how do these hierarchical algorithms actually decide which clusters are closest and should be merged? Well, they use what's called linkage criteria. Single linkage looks at the minimum distance, meaning it measures the gap between the two closest points in two different clusters. Complete linkage looks at the maximum distance, measuring between the two furthest points. An average linkage, as you might guess, calculates the average distance between all points in both clusters. Changing your linkage criteria will literally change the entire shape of the tree you build. Section 4. When you don't know K. Dynamic discovery. So far, we've seen some pretty powerful algorithms. But there is a massive narrative twist in unsupervised learning. What if you don't know the number of clusters, your K value, in advance? Algorithms like K-means force you to guess K before you even run the program. But in true exploratory data analysis, you often have absolutely no idea how many patterns are hiding in your data. So what do you actually do? Well, you use dynamic no-K methods. We have some fantastic alternatives here. We already talked about hierarchical clustering. With that one, you just build the whole tree and then cut the dendrogram at whatever distance threshold makes sense after the fact. But then we have dbScan. dbScan is incredible. It groups data purely by density. You just give it a neighborhood radius and a minimum number of points, and it dynamically forms clusters wherever data is densely packed, completely bypassing the need for a predefined K. And even better, it labels sparse areas as noise, basically ignoring outliers entirely. There's also mean shift, which simply shifts points toward regions of highest density until they converge, and Gaussian mixture models, or GMM, which assumes data is generated from a mixture of distributions and uses information criteria like BIC or AIC to evaluate and automatically select the optimal number of clusters for you. Section 5. K-means versus K-nearest neighbors. Clearing the confusion. Okay, let's take a second to clear up one of the most common and frankly frustrating naming confusions in the AI world. K-nearest neighbors versus K-means clustering. Because they both start with K dash, people mix them up constantly. But at their core, they belong to entirely different families of machine learning. K-nearest neighbors, or KNN, is a supervised learning algorithm. It strictly requires labeled training data because its entire purpose is to predict a label or value for a new data point by looking at its closest neighbors. K-means clustering, as we've learned today, is an unsupervised learning algorithm. It requires absolutely zero labels and just looks for structure and groupings in raw data. Their computational trade-offs are also exact opposites. K-nearest neighbors is what we call a lazy learner. It has almost no explicit training phase. It just kind of memorizes the data. But when it's time to actually make a prediction, it is highly computationally expensive because it has to calculate the distance from your new point to every single other point in that massive data set. K-means execution is the total reverse. It has an iterative and sometimes heavy training phase to find those perfect centroids, but once it's trained, it is highly scalable and lightning fast at assigning new data, simply because it only has to measure the distance to the K centroids, not the whole data set. So the absolutely crucial takeaway here is this. Despite all their differences, supervised versus unsupervised, lazy versus iterative, both of these algorithms share one critical dependency. They both rely entirely on distance metrics, like Euclidean or Manhattan distance. Because they measure physical space between data points to make their decisions, feature scaling, like normalizing or standardizing your data, is absolutely critical. If one feature is measured in millimeters and another is measured in miles, your distance calculations are going to be completely distorted and both algorithms will flat out fail. We've covered a lot of ground today, all the way from the flat partitions of K-means to the dense neighborhoods of dbScan. But I want to leave you with a final thought to ponder. If these clustering algorithms are powerful enough to blindly find hidden structures, shapes, and rules in entirely unlabeled chaotic data, what unknown patterns are hiding in your own datasets right now? Whether it's customer behavior, server logs, or even personal finances, the structure is there. It's just waiting for the right algorithm to crack the code. Thank you so much for joining me on this explainer, and keep exploring your data.